This is an example of calculating the largest panel size for collecting rainwater in a situation similar but not the same as the task. If you have a look at the rainfall, we have here the usage that people have. So it starts off at about 160 in January and February, goes to about 140, it looks like it drops down a little tiny bit there, goes up to a maximum of 180, etc, etc. So this here is the usage that people have. This is how much they need to drink and shower and clean. This is how much rain is falling on the town in any given month. So here we've got January, February, March, then we've got April, May, June, July, August, September, October, November, December. And I've already got marked here. If I take this point here, that's 180. That's the most water that gets used by anybody. And it coincides with May, and May is in here, April, May, June. So it's 3.3 millimeters of water falls every hour, each day, for the whole of the month of May. So the questions that we want to look at are: what is the biggest collection panel needed? And we've got 180 litres required per person, that's from here. And we've got 3.3 millimeters falling per hour, and we've got that from here. Remember, the graphs on your task are different, so the numbers are slightly different, but I'm showing you the method. We're going to be dealing with a few different types of units. We'll be dealing with volume, we'll be dealing with capacity, which is measured in milliliters, and we'll be looking at lengths. We're looking at centimeters cubed for volume, millimeters cubed for volume, meters cubed for volume. For capacity, we're mainly looking at milliliters. We'll be talking about liters also. If you get a lot of very large capacities, you will talk about kiloliters, but we're not talking about that today. So let's move on. So here we go. The maximum panel size when usage is the highest and rainfall is the lowest. Now, rainfall isn't the lowest in our case because our usage is actually, we know exactly when our usage is. It's in the highest when it's in May, so we've got to use May to measure it by here. As it happens, that's the lowest bar, but if it wasn't the lowest bar, we'd still have to use this value here because we know that the maximum usage is here. So you'd need to describe that in your task. So the highest usage in May is, let's say, use the capital letter U, usage max per person is 180 litres per person per day. So let's have a look at the rainfall. The rainfall at the time of the highest use is in April to June. That's that bar on the bar chart. So therefore the rainfall is equal to 3.3 milliliters per hour. So we haven't found anything new here, we've just rewritten it. Now let's do a conversion. Let's convert our usage into per day usage. At the moment it is per person per day, but we know we've got 112 people that we want to look after. So that's 180 times 112. So that gives us this number, 20,160 litres per day. Now this is for everybody. So that's why it says max total. Also, let's convert our rainfall into per day. I ran out of room here, so I've gone on to the next slide. So, next slide. Usage, maximum, that's what we calculated before, 20,160 litres per day. Let's do the rainfall conversion. Rainfall per day is 3.3 millimeters per hour. You multiply that by 24 hours per day, you end up with 79.2, and the units end up being in millimeters. Basically just multiply 24 by 3.3. Now I've converted, look here, centimeters. The reason why I'm going towards centimeters is I know that centimeters cubed is very useful. 7.92 centimeters, so I moved the decimal place 1 because I did a divide by 10 because there's 10 millimeters in a centimeter. So if the rain didn't flow away and all collected on the panel, it would collect to a depth of 7.92 centimeters each day. Now we know it flows away, but if it did collect, it would end up being 7.92 centimeters deep. So on a 1 centimeter cubed area, the amount of water, which is, we're talking about volume now, would be, the volume of a day would be 1 centimeter squared, that's the area it's falling on, times 7.92 centimeters deep, and that makes 7.92. We're now talking about centimeters cubed, so that's the volume that would collect. So that's working out on 1 centimeter cube. So let's have a look here. 7.92. This piece here is a repeat of the previous slide. So let's go to here. So on a 1 meter squared area, instead of centimeters squared, I know that 1 meter by 1 meter, if I made that into a square, would be 100 centimeters and 100 centimeters. So that makes 100 times 100, or 10,000 centimeters squared that fit on a 1 meter square. So in order to go from here, I've got to say, if I've got on a 1 meter square, I need 100 times 1 centimeter cubes, because these are tiny and the meter is big. So I need 7.92 times 10,000, which gives me 79,200 centimeters cubed of water in a day. So that's the volume that I get in a day. Volume on a 1 meter squared area. We know 1 centimeter cube can be filled with 1 milliliter of water. This is why it's really good to work in centimeters cubed, because I can use the 1 milliliter conversion. So now I'm going to go from volume here to capacity, because capacity is measured in liters and milliliters. Capacity, so C of a day of rain, is 79200 milliliters, because it's exactly the same number as in centimeters cubed, because I've stated the conversion here. Now I'm going to convert it into liters. I know that there are 1,000 milliliters in a liter, so that's divide by 1,000. So move the decimal place 1, 2, 3. I end up with 79.2 liters per day on a 1 meter square. So this, we're getting somewhere now. We now know how much can we collect on 1 meter square. The next step is to find out how many meters we need, how many meter squares we need in order to get all of the water that we need. So let's go here. So I've just rewritten up here. So the capacity in a day is 79.2 liters from a 1 meter squared area, but we need 20,160 liters for all the people. So the area maximum will be the total number of liters that we need divided by how many liters fall on 1 meter squared, and that'll tell me how many meters squared I need, because I need a big panel. So that comes out to be 254.5454, and it keeps going 545454. So you can either write that with a dot on the 5 and a dot on the 4, or sometimes they use a bar between the two numbers, between the start and the end of the recurrence. Right, the units in this case are liters divided by liters over meters squared, which means that the liters cancel. You end up with meters squared, which is great because that's what we wanted. We wanted the total number of meters squared. That's just a double check of the units to make sure my units are correct. So my maximum area of the panel is going to be 254.55, so 254 and just a bit over a half meters squared. So what does that mean? That means my panel can be 2.54 meters wide, which is a bit longer than a really tall person. So I'm 1.8, so it's a bit taller than me is wide, and then it's 100 meters long. Or you can double that and have it 5.8 meters high, or sorry, wide, and have it 50 meters long, or any other combination you like. You could have more than one panel and divide it up, but all of the panel has to make 254.55 meters squared in order to give enough water from the most usage situation, which was back here. So we need to get 180 liters per person, and we did that calculation and we worked out 20,160 liters per day. So to do that we need 254 square meters of area for our collector. So that's our main calculation. These sheets will be on the OneNote and this video, obviously you can stop and start and see if you can follow it through. I've done it really quickly. Ask me next time we catch up with each other if you still are having problems with this calculation. Bye, see you soon.